So what these orders of magnitude actually help transition you into is the talk of logarithms. Logarithms are basically the opposite or the inverse operation of exponential functions. Right now, you're going to focus on log base 10, known as a common logarithm, and exponentials with a base of 10. As you move into the next chapter, you're going to start dealing with other bases as well and deal with more situations where other logarithms are going to be used in the long run. So basically what this is all asking, these are all common logarithms. If you don't see a base down in this subscript position, it's always assumed to be base 10. And so what each of these are essentially asking is, what power of 10 is this number here? This number here being a million. What power of 10 is this number here? So forth and so on. So basically, if you want to be able to do this without a calculator, then you should be kind of trying to figure out, well, this number here is equal to 10 to what power? And this gets us back to stuff that you learned at the beginning of chapter 4. And essentially is, okay, well, you know this is a larger number, so this is going to be a positive exponent on the 10. There's 6 zeros here, so this is 10 to the 6th power, which means that the log of 1 million is going to be 6. This one here, the log of 0.000001, well, how would you write this as a power of 10? It's a smaller number, so you know this is going to be a negative exponent. You need to move it 1, 2, 3, 4, 5, 6 decimal places to get it to the position of 1. So you know that this is going to be 10 to the negative 6th power. So the common logarithm, or log base 10, of this number is negative 6. This one here has 9 zeros, so you're talking about 1 billion. So how would you write that as 10 to a power? Well, because it has 9 zeros to it, this is going to be a positive 9 exponent, which means this is going to be 9. And finally, this one here, the 0.0001, this is like having 10 to what power? Well, that's 4 decimal places you have to move to get it back to the 1 position. So 10 to the negative 4, which means that the logarithm, the common logarithm that is, of 0.0001 is negative 4. And oftentimes when you're dealing with situations like this and you're asked to basically answer a question like this, now you could do this on a calculator because the most calculators in the TI-83, 84 that you've been recommended for this course has a log button on it. However, they still want you to kind of figure out what this is equivalent to saying. And essentially, this statement here, log base 10, it's not written, but it's assumed, of 800 is 2.9031. Well, remember, this is like saying, well, 10 to what power equals 800? So the 800 is going to go here, the 2.9031 is going to go here. So essentially, that's the exponent of 10 that you would need to raise it to end up with approximately 800. Now, a lot of times when you're doing logarithms of numbers that aren't perfect powers of 10, you're going to have irrational numbers again. So a lot of these decimals are going to be approximates, and so that's why you're going to see the wavy equal signs, because if you actually put this into a calculator, you'll get something close to 800, but it might be a little bit under or a little bit over depending on the situation and how you round it. So likewise for this, it says, without using the common logarithm key on your calculator, estimate the value of the following, round your answer to 2 decimal places. And so this one would require you to show some work, and if you're asked to do a similar problem, like on a quiz or something like that, then you would have to show some work with this. So 8,500 is not a power of 10. It's between 2 powers of 10. It's between 10 to the 3rd power, which is 1,000, and 10 to the 4th power, which is 10,000. So it's definitely between these two, and probably a bit closer to 10 to the 4th power. So right now, if I had to guess what it's between or what it's approximately equal to, it's somewhere between 3 and 4, possibly a little closer to 4. So using that information, I look at 10 to raised to the 3.9 power. That's 7,943.28. So this is less than at 8,500. So on the lower end, I could say that, okay, well, now this is the lower end here. It's between these two values, which are a lot closer together. So now I want to start working on the second decimal place. So I start with 10 to the 3.91 power. And I get about 8,128.31. There's more decimal places, but it's still smaller than this. So I know this now goes towards the lower end. I try 10 to the 3.92 power, I get 8,317.63, which is still smaller than this. So that now takes the place of the left-hand side. And then when I do 10 to the 3.93 power, I get 8,511.38. This is now bigger than this value here, so I now know that 8,500 is somewhere between 10 to the 3.92 power and 10 to the 3.93 power, a lot closer to the 10 to the 3.93 power. Because of that, and the fact that this is looking for the exponent I would raise 10 to get 8,500, this should probably be about 3.93. Again, because 8,500 is a lot closer to this than it is to this. And so that's how you would estimate it without using the logarithm key on your calculator. Even with the logarithm key on your calculator, answering a question like this would be a little bit tough because you're saying, okay, well, the log base 10 of what is 2.907? And you could try to guess a lot of numbers, but they may take you a while. However, if you want to think about what this is saying, oftentimes when you have an equation involving a logarithm or an exponential, it's better to write it in its inverse form. So what exponential statement can I write that's the same as saying this, but might make it a little easier for me to figure out what x is? Well, going back to some of the previous examples, this is a base 10 logarithm, so I know that 10 raised to this exponent should equal this x value. And then all I have to do is put this in the calculator. And if I do that, I get about 807.235. You were asked to round to the nearest integer, and so you would round this to about 807. And so that is the end of this problem, and that is the end of this video. If you have any additional questions, please make sure to bring them up during class.